Hello everyone. We are glad to present our paper, Interactive Class-Agnostic Object Counting. Visual counting is an important task that has a wide application, like component counting for assembly line efficiency in manufacturing, crowd counting for public security, and car counting for traffic management. Class-agnostic methods offer a promising avenue for counting diverse objects in the wild. These methods enable users to specify an exemplar for the category of interest, utilizing spatial similarity for density estimation. However, they grapple with challenges stemming from imprecise similarity metrics affected by various factors such as object size, shape, and color variations, along with large density and object occlusion, leading to a number of inevitable errors. Recognizing the challenges in existing visual counting works, we introduce an interactive framework designed to leverage user feedback for enhancing the accuracy and performance of the visual counter. The proposed framework allows a human user to quickly detect mistakes and improve performance based on the identified errors. As illustrated in this framework, an interactive computer vision system comprises three critical components: results interpretation, feedback collection, and model adaptation. Contrary to tasks such as object detection or segmentation, designing these three components for visual counting presents unique challenges. Our main contributions are threefold. First, we introduce a density segmentation technique: segment the density map into multiple regions for interpreting the result. Second, we propose a user-friendly feedback collection mechanism that requires just 2 clicks. Finally, we develop an effective adaptation strategy to adapt the visual counter. We introduce iterative peak selection and expansion to segment density maps. The segmentation is guided by 4 key considerations. First, each region should be non-overlapping. Second, the regions should collectively cover the entire density map. Third, each region should maintain integrity and have a limited integral value. Finally, each region should be of moderate size. First, we smooth and downsample the density map. Next, we iteratively pick the highest density pixel as a peak and expand it into a region. In the expansion phase, we aim to minimize an objective function with 3 terms. The first for integrity, the second for moderate size, and the third for limited object number. Fortunately, only a sufficiently good solution is needed for this minimization. After segmenting the density map into regions, we offer predefined ranges for each. Users can then select a region and choose a corresponding range as feedback. For visual counter adaptation, rather than adapting the entire counter's regression head, we introduce a feature refinement module. During adaptation, only this module's parameters are updated. It consists of 2 components: channel-wise refinement for each channel and spatial-wise refinement for each spatial position. Our adaptation loss constrains each selected region's prediction to fall within the provided range. We consider 2 cases: treating each region individually and treating them collectively. The final loss is an average of these 2 terms with a regularization term. To improve time efficiency, we adjust the learning rate and adaptation steps based on feedback confidence. Our first assumption is that more feedback equates to higher confidence. Thus, the first term in our confidence metric simply reflects the quantity of feedback. Our second assumption is that less inconsistency in feedback correlates with higher confidence. This addresses typical failures arising from local-global error discrepancies. We measure this inconsistency among feedbacks and incorporate it as the second term in our confidence metric. The final confidence is the average of these 2 terms, which we use to adjust both the learning rate and adaptation steps. Here's a quick demo of our framework, where just a few interactions significantly improve the visual counter's predictions. Each interaction only requires 2 clicks, the same with drawing a bounding box for a new exemplar object. Results on FSC 147 and FSC DLVIS demonstrate that our framework substantially enhances the performance of the visual counter. For more details, please refer to our paper. The qualitative results demonstrate that our interactive counting framework can reduce errors both globally and locally. The left is before 1 interaction, and the right is after 1 interaction. In the shown qualitative results, the highlighted region is the selected region in interaction. Our project is available on this link. Thank you.